Say you were floating towards the black hole. Basically, the first part of you that was starting to get closer and closer to the black hole would start to experience the really extreme gravity that was near the black hole. Your body would basically start to be stretched like a spaghetti, stretching to get into the black hole where we would never see you again. Once you're in, you're stuck, and that becomes your universe.
This is NASA's Curious Universe. Our universe is a wild and wonderful place. I'm Patty Boyd, and in this podcast, NASA is your tour guide. This week's adventure will give you a front row seat to some of the universe's most perplexing wonders. We're exploring black holes.
Really, these are some of the most extreme environments in the universe.
That's Regina Caputo. She's an astrophysicist at NASA, and she studies black holes, mysterious and fascinating cosmic objects.
We can't make anything like a black hole on Earth to study it. And so if we really want to understand how gravity interacts with all of the other forces in the universe, it's really a playground for understanding how gravity works, how fundamental particles work, how stars collapse in on themselves.
Black holes truly are one of a kind. But what exactly is a black hole? Let's start with the word black. The name comes from the fact that nothing can escape the gravity of a black hole, not even light. How can they keep such a tight hold on everything? Well, they are extremely massive.
And so they have very strong gravitational attractive forces. And so they really don't suck things in, they pull things in, because that's how gravity works. It's things that have mass are all attracted to each other.
And the more mass, the more gravity. Even though light travels so quickly, it is no match for the gravity of a black hole. So now you know why they're black. Let's talk about why they're called holes. This is actually a misleading word to describe these massive objects. While they may seem like a hole in the sky because they don't produce light, a black hole is not empty. It's actually a lot of matter condensed into a single point. This point is known as a singularity. So how do we get such a large amount of mass to come together at one point in space? Step 1, get yourself a large star.
Big stars burn up their fuel really fast because they have more gravity, which makes the centers of them hotter and denser, so they can go through a lot more nuclear reactions, and they burn it all up really, really fast.
That's Jeremy Schnittman, a research astrophysicist at NASA. He's going to explain how a star gives rise to a black hole as it eats up its fuel.
They build up a big pile of ashes in the center of the star. Those ashes, actually, it's iron. That iron doesn't do nuclear burning, so it doesn't give off extra heat, and it just sits there, and it's getting bigger and bigger and bigger.
And now you have these two forces that are battling against each other. One force comes from whatever fuel is left to be burned, and another force is from the gravity of the iron pulling everything inward.
And eventually you run out of this pressure that's holding up the center of the star, and the gravity just keeps getting bigger, and the pressure stays more or less the same, and so the gravity wins. When the gravity wins, everything just starts collapsing.
At that moment, two things are happening. Some star stuff is being shot off into space, causing the light shows we call supernovae. And the rest of it condenses into one point, the singularity. And that is how you make a stellar mass black hole. It's called stellar because it was made from a star. Our sun is a star, so you may be asking, will it ever become a black hole?
As far as our sun becoming a black hole, it's unlikely that our sun is massive enough in order to actually become a black hole.
Our sun will never form an iron core massive enough to collapse into a black hole. In fact, the smallest black hole we've ever observed was about 4 times the mass of the sun. Instead of a black hole, our sun will evolve into something else.
At some point in our sun's lifetime, it will puff up into a red giant phase, and so it'll get really, really, really big. Future humans will have to deal with that, but it's very, very far in the future.
By far in the future, Regina means really far, about 4 billion years. If our sun were magically replaced by a black hole of the same mass, here's what would happen. Earth and all of the other planets would stay in their same orbits, experiencing the same amount of gravity as before.
We wouldn't even notice, like the Earth would still rotate around.
The major difference? No light. A solar system in darkness. Not a fun scenario. So Jeremy took you through the birth of a stellar mass black hole. But that's not the only kind of black hole that we know of. There's another kind of black hole that makes a stellar mass black hole look like a blip in the universe.
There are these supermassive black holes that are millions or even billions of times more massive than the sun. And those are in the centers of almost every galaxy. We still don't really know where those come from, but they seem to be quite universal.
In fact, we have one of these mysterious giants at the center of our galaxy. About 26,000 light years from Earth, the equivalent of 150 quadrillion miles, is the Milky Way's supermassive black hole called Sagittarius A star. It's called that because it's located in the constellation Sagittarius. And you might be surprised to know that it wasn't discovered until 1974, which raises the question: if you were hunting for a black hole, how would you know when you had found one? After all, they are black.
You can't actually see a black hole because they don't produce light like stars do.
However, black holes can be some of the brightest objects in the sky. That's because of what can happen before black holes gobble up star stuff. Around a black hole is a boundary called the event horizon. Anything that passes the event horizon is trapped within the black hole. But right as the gas and dust get closer, the gravity from the black hole makes them spin really fast, forming lots of radiation.
So we see that last little bits of light escaping from the event horizon.
Another clue that there is a black hole is when you see a star orbiting what appears to be nothing at a very fast pace. That's how Cygnus X1, the first ever confirmed black hole, was found in the 70s.
We saw this star orbiting around something, and we didn't know what it was orbiting around. There were a lot of X-rays coming from it, and figured, well, the only way it could be moving that fast is if there's a really strong gravitational field pulling on it. Since there's really nothing else that it could have been, and it was more or less invisible, that's how we concluded that it was in fact a black hole.
Cygnus X1 was a big deal. Finding it confirmed what until then had only been a mathematical prediction based on Einstein's theory of relativity. Since then, we've found black holes through other means. Like sometimes a black hole can reveal itself if it comes between Earth and a bright star.
Gravity actually bends light, bends the trajectory of photons.
The gravity of the black hole bends the space surrounding it, so the light from the star travels through this warped space and looks very strange, kind of like a cosmic donut. It's a phenomenon called gravitational lensing. And finally, there's one more way we can detect black holes. One that requires that two black holes get very close to each other.
And then they start orbiting around each other and basically get closer and closer and closer and closer together as they're spiraling towards each other. And at some point, their event horizons merge and they smash.
The process literally shakes the fabric of space-time. We've observed this before, and in some ways we've heard it too. We've detected these waves with LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is funded by the National Science Foundation and operated by Caltech and MIT.
That smashing together of these very, very massive objects sends out ripples in space-time. And those ripples are just like sound waves, and LIGO is built to detect those ripples.
Scientists took those ripples and translated them into audio waves so that we can hear it. Take a listen. First, you'll hear the sound at the original frequency corresponding to the gravitational waves. Now here is the sound played at a higher frequency that is easier for us to hear. Did you hear the whoop? That was the waves getting faster and faster as the black holes merged.
And so that's how we get the sounds of the universe.
All of these ways of detecting black holes require that some other object be present. But if the black hole is flying solo, with nothing nearby orbiting it and nothing nearby to eat, there is little chance that we will ever notice it. We will likely only get to know a fraction of the millions, if not billions, stellar mass black holes that are estimated to live in the Milky Way alone. Stellar mass and supermassive black holes are vastly different in mass. And for a while, scientists thought there might be no black holes with masses in between these two extremes. But recently, with the help of the Hubble Space Telescope, astrophysicists found the best evidence yet of intermediate mass black holes. NASA's Chandra and NuSTAR telescopes have also been exploring these newly discovered middleweights. Now it's time for us to explore a black hole up close and personal. Let's take a journey into one.
Say you were floating towards the black hole.
Now let's suppose that you are approaching a stellar mass black hole, and that it isn't actively consuming star stuff, because if it were, even being near the black hole could be deadly.
I certainly would not want to be in the path of a black hole that's actively eating up these stars. They eat things and then they kind of burp up particles, at the speed of light.
Lots of high energy particles do not mix well with life. So let's just assume you approach a lonely black hole by chance, because you wouldn't see it. Now, as you get closer, all of a sudden, you start feeling this tugging on one side of your body, but not on the other.
Basically, the first part of you that was starting to get closer and closer to the black hole would start to experience the really extreme gravity that was near the black hole. Say if you were going feet first, your feet would start to be stretched apart. Your body would basically start to be stretched like a spaghetti.
There's even a technical term for it. It's called spaghettification. Basically just rip you to pieces.
You probably wouldn't survive.
But just for fun, let's say you did survive.
Part of you would cross over into the event horizon, and the rest of you would probably be following pretty soon after.
This only happens with stellar mass black holes, where you can feel that change in gravity. But if you found yourself entering a supermassive black hole, you wouldn't feel a thing. All of a sudden, you would just be inside the black hole, never to be seen again. Well, kind of. Here's the crazy part. If your friend were watching this happen to you, they might see you get stretched, but it would happen really slowly, until at some point it might look like you were frozen in time, like you never passed through the event horizon. That's because time gets stretched out by the immense gravity that a black hole produces.
Really, it bends the reality of our universe.
And the reverse happens from your vantage point. So if you were looking out at your friend, it would seem like they were moving through life at warp speed. If somehow you weren't ripped apart by the gravity, or managed to survive the radiation near the black hole's event horizon, well, then you would get to enter the black hole.
Once you're in, you're stuck, and that becomes your universe.
What would you see and feel? We don't really know. We can only theorize. But at some point, you would become one with the singularity. Essentially, you'd be compressed into a tiny speck.
So I would not recommend traveling to black holes. At least not that close.
And luckily, it shouldn't be too tricky to avoid them. The nearest black holes we know of are thousands of light years away from us, meaning it would take thousands of years to get to them if we could travel at the speed of light, which we can't. So not only will they not be eating Earth, they're too far away for a visit from Earthlings. By now, the universe is peppered with black holes, with new ones forming all the time. And some black holes keep expanding as they consume more gas. But how and when does a black hole die?
Even the ones that are creating hot gas and are very bright, they only do that for a very short part of their lifetime. But eventually they'll all just run out of fuel. Even if they have a star orbiting around them, that won't last forever. There's nothing left for them to do. They're just gonna sit there.
And for the most part, all of the matter inside the black hole will stay there as well.
What happens in a black hole stays in a black hole.
There's only one theorized way that anything can escape a black hole's gravitational grip.
There's an interesting result from Stephen Hawking, the famous theoretical physicist, who showed that because of these quantum mechanical effects, a tiny bit of radiation can actually leak out of a black hole. It's called Hawking radiation. But in practice, it's such a tiny, tiny, tiny effect. First, we will never be able to observe it. And second, if you have a star that's 10 or 15 times the size of the sun, it would take trillions and trillions of years before it even changed a little bit because of the Hawking radiation.
Once you hit black hole, you're black hole for the rest of the universe, it seems like.
The long-lasting nature of black holes leads scientists to speculate that towards the end of the universe, when there's no stuff left to make new stars, and when all of the existing stars have burnt up, the universe will be dominated by black holes, a dark and uninviting scenario. Until eventually, those dissipate trillions upon trillions of years later, more time than we can fathom. And then, there will be nothing. This is NASA's Curious Universe. This episode was written by Margot Wall and Maddie Arnold. The Curious Universe team includes Michaela Sosby and Vicki Woodburn. Our executive producer is Katie Atkinson. Special thanks to Claire Andrioli, Ryland Heggie, Barb Matson, Erin Cara, and the astrophysics team. If you liked this episode, please let us know by leaving us a review, tweeting about the show at NASA, and sharing us with a friend. To keep up with the latest black hole science from NASA, check out nasa.gov/blackhole. Still curious about NASA? You can send us questions about this episode or a previous one, and we'll try to track down the answers. You can email a voice recording or send a written note to nasa-curiousuniverse@mail.nasa.gov. Go to nasa.gov/curiousuniverse for more information. Thank you for listening to the second season of NASA's Curious Universe. We've enjoyed taking you along with us as we've explored everything from the International Space Station to our asteroid hunting mission. We're taking a break now, but we'll be back before you know it. Until then, you can continue exploring the universe and discovering our home planet with NASA by visiting nasa.gov. You can also follow NASA on Twitter, Instagram, and Facebook. And find more NASA podcasts in your app or at nasa.gov/podcasts. Before we sign off, we've asked our scientists to do their best impression of the sounds we can make from black hole data. Here's what they gave us.
Whoop, 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 whoop.